My name is Didier Ishime. I'm from the University of Nebraska-Lincoln. Today, I would like to introduce to you our work on Dynaplex, a tool for inferring asymptotic runtime complexity of recursive program. Complexity analysis is important for developers to help them detect performance vulnerabilities. Complexity analysis can also help developers optimize the performance of their programs or software. Dynaplex uses dynamic analysis to infer recurrence relations and solve them for runtime worst-case complexity. Recurrence relations, also referred to as recurrences throughout the presentation, are mathematical relations showing how to solve a problem in terms of solving its subproblems. For instance, selection sort, which is a sorting algorithm that sorts n elements by recursively sorting n-1 elements using at most n steps per recursive step. We use recurrences because they are even linear recurrences, which are simple enough, are expressive enough to capture non-trivial program complexities. For example, binary search has a linear recurrence of divide and conquer recurrence, which solves to logarithmic. Karatsuba solves to an irrational degree, and Hanoi can solve to an exponential complexity. Babasort have quadratic complexity. All these different classes of complexity are expressed using linear recurrences. I would like to give an overview of how Dynaplex works, of the architecture of Dynaplex, before we get into the tool usage of Dynaplex. Dynaplex works by analyzing traces collected by instrumenting a source code of a program and running that program on random inputs to produce those traces. Those traces collected are then analyzed to infer recurrences and polynomial relations, which are then solved using master theorem and other pattern matching techniques to produce the worst case runtime complexity. Let's look at an example of how Dynaplex infer these recurrences. On the right, we have merge sort program, traces collected by running merge sort program on a list of size element. At each node, we have two values, n and id. N represents the size of input at that recursive call, each node corresponding to a recursive call. And id represents to the unique id of the recursive call in order to be able to produce the tree. As you might all know, merge sort sorts a list of elements by recursively splitting the list into two halves and recursively calling merge sort on those two halves. So for example, here we have 7 is divided into 3 and 4. 4 is divided into 2 and 2, and so on. So once Dynaplex has these traces, it computes the ratio between the size of input at each node and the size of input at its child node. So for example, with the left child nodes, we have 7 divided by 3, 3 divided by 1, 2 divided by 1, 2 divided by 1, 4 divided by 2, and so on. With the right ratios, we have 7 divided by 4, 3 divided by 2, 4 divided by 2, and so on. Dynaplex uses regression to compute these ratios. So for example, the left ratio tends towards 2, 7 divided by 3, 3 divided by 1, 2 by 1, 4 by 2, and so on. And the right ratio converges towards 2 also. At this point, the recurrence relation is Tn equals 2 Tn over 2. This 2 represents the number of recursive call, which also equals to the number of child nodes per node. The Fn represents the relationship between the size of input and the number of loop iterations. And this can be calculated using polynomial regression. In this case, the number of loop iteration is linear in terms of the size of input for merge sort. And after computing Fn, we have the complete recurrence relation for merge sort. This recurrence relation can be solved using master theorem, which results into n log n. Now that we have an idea of how Dynaplex works to produce the recurrence relations and solve them for complexity analysis, let's discuss how Dynaplex is used. First, I would like to talk about some design decisions. Dynaplex is implemented in Python and uses regression to learn polynomial relations. Dynaplex is language agnostic. It can analyze programs written in any language, as it runs on traces, not the source code of the program. We will see this in more details later on in some examples. To use Dynaplex, all you need is a computer that can run Docker, and you can pull the image from Docker Hub using this command and run the container using the docker run command. As I said earlier, Dynaplex runs by analyzing the traces, and traces are collected in the trace folder. So Dynaplex runs by analyzing, it takes input a trace folder that contains all the traces. Since traces are a major part of Dynaplex, I would like to discuss how traces are collected. First, we instrument the source code of a program to collect the size of input and depth of recursion at each recursive call. We also collect the number of loop iterations for one recursive call, and these traces are saved in files using naming convention that we'll discuss a little bit later on, and that can also be found on Dynaplex's GitHub repo. Let's show an example of how this works. Here we have a C++ implementation of pancake sort. To instrument this program, we use a C++ library we wrote for instrumentation, which is included on line 1. We also need to specify the problem size at the function entry of the function to analyze. For each loop or for each auxiliary function, we instrument the loops to track the number of loop iteration. Now, we have a script to run pancake sort 100 times using input with size randomly taken from 1 to 500. And the seed is saved for reproduction purposes. So the traces are collected in this folder, pancake sort, and as I said earlier, the naming convention is output dash size of the input used to produce those traces. So we have here multiple traces, each one with the size of input that are used to produce it. We run Dynaplex on pancake sort, and the output of Dynaplex can be divided into 3 parts. First, we compute the recursive terms of the recurrence relations, which here for pancake sort is tn-1. Then we compute the polynomial relation describing the relation between size of input and the number of loop iteration. These polynomial models can be computed up to a max degree, which can be specified by the user. And by default, it's 5. And after computing the polynomial relation, we apply heuristics, which are explained in our technical research paper published at UPSLA 2021. For pancake sort, we find that there is a linear relation between the number of loop iteration and the size of input. And the third part is we combine the 2 terms, the non-recursive term with the recursive term, into the complete recurrence relation, which is then solved using some pattern matching techniques to produce the worst case complexity of pancake sort, which is quadratic. As I said earlier, Dynaplex can run on programs written in any language. Thus, we might not be able to use the C++ library for instrumentation. So in this example of insertion sort, I will show you how to instrument a program to collect the necessary traces for analysis. First, at the function entry of the function to analyze, we instrument the program to collect the depth and size of input, the depth of recursion and the size of input. And for each loop we keep track of the number of loop iteration for one recursive call. The traces are saved in using file naming convention output dash size of input. And then we run the program a few hundred times to produce enough traces for the analysis. Again, you can run the analysis by giving analyzer the path to the trace file, to the trace folder. And in this case, we compute the non-recursive term, the recursive term, the polynomial relation, which are combined into the recurrence relation, which is then solved to give the quadratic complexity of insertion sort. In conclusion, Dynaplex takes as input trace files and produce the worst case complexity of a program. To use Dynaplex, you can download its Docker image from Zenodo. There is all instructions needed there, or you can download the source code from GitHub and follow the instructions in the README on how to install dependencies. More details on this demo can be found in our demonstration paper published at Icse 2022, and more technical details can be found in our research paper published at Uppsala 2021. Thank you so much for your attention.